So now I'm going to tell you everything about liquids, solutions, in general, the reactions that happen in liquids and solutions, and how they are related with other phases, that is gases and solids. So basically, phase changes, the thermodynamics of all that. So let's start. So the first thing is called solubility. This is not very important for the whole note, but yeah, let's just deal with this. Solubility is defined as the apparent molarity of a solute in a saturated solution. So the solution that is at equilibrium. And what do I mean by apparent molarity? That is the moles of solute dissolved, not the moles of solute present in the solution. Instead, it's the moles of solute dissolved upon the volume of solution. And that's why I call this apparent molarity, because it's not the actual one. Okay, next we basically state what Henry's law and Rod's law is. Later we are also going to prove them and figure out what are the differences between them. So Henry's law, for gas dissolving in liquid, the solubility that is given by some constant, we call that Henry's constant, times the partial pressure of the gas above the liquid. Then for Raoult's law, or however you pronounce this, we have this equation P equal to x p naught, where P is the partial pressure of liquid's vapors, x is the mole fraction of liquid in solution, and P naught is the vapor pressure of pure liquid at that temperature. And both these laws, they are not the same. I mean, you might think, what's the difference between Henry's law and Rod's law, except that this looks more general, because the Henry's constant, it could be anything. And for Rod's law, we have a specific constant, that is P naught, which is measurable and stuff. So it looks like Rod's law is just a consequence or a special feature of the Henry's law. But that's not correct. So these are applied in two different cases, and there is one case when both of them are the same thing, but we'll talk about that later. So for non-ideal, for real liquids, real solutions, these two laws are different. So Henry's law, we apply that when we want to measure things for dilute solutions. So for just the gas dissolving in liquid, there will be a dilute solution that will be made, because the gas, it's not that there is a big quantity of solute in the solution already and then that's going away. No, instead gas is dissolving into the solution. So for that, you can take the solution to be dilute, and that's when we apply Henry's law. When the mole fraction of the solute, or whatever substance you are taking, that thing is very small, as this mole fraction becomes bigger, we start to get deviation from Henry's law, and then we somehow go to Raoult's law. So Raoult's law, it's a much more uh, it's a much more general law, and by general I mean that it is applied for a vast region of this curve. So for many different values of x, we can apply Raoult's law. So basically, Raoult's law, it relates the vapor pressure of a particular liquid in a solution, and it relates it with the mole fraction, of course. So you have either positive deviation or negative deviation from Raoult's law, and it's pretty clear why these names are like that. And then you have something called ideal solutions. And for ideal solutions, both of these things, Henry's law and Raoult's law, they are the same. And we will learn what ideal solutions are in a bit, but just know that for ideal solution, this graph just becomes a line. Now I will explain why Henry's law works, that why do we expect this kind of linear curve at the very start of this graph. So when we take a dilute solution, the solute can be treated as if it was an ideal gas. Yes, it can be treated as if it was an ideal gas. You heard me correctly. So for that, we can write this equation PV equal to nRT, just modified a little with different symbols. And then we can do some thermodynamics. So for a certain temperature T, the change in the Gibbs free energy of the solution, or I should say of the solute in the solution, that is the volume of the solution times the change in pressure. So the whole formula is dg equal to vdp minus sdt for reversible processes, but then for certain temperature your dt is 0, so it just becomes dgs equal to vs d pi. In this case, pi is the pressure exerted by the solute that we are considering to be ideal, as ideal gas, on the walls. So the pressure exerted by the solute on the walls of the container, that thing we are considering as pi. I know it doesn't look good, we should have took p, but pi also works, whatever works for you anyway. So dgs equal to vs, and this subscript s, it means solute in solution, and I will explain whatever the subscript means. Sometimes it might not be clear from what I've written, but I will try to explain that. So it's VSD pi, and since it's modeled as an ideal gas, we can of course apply the ideal gas equation. So ideal gas law, it says that PV equal to nRT, so V is nRT upon P, in this case nRT upon pi, and then from that we can integrate this to give a general expression for this. So Gs equal to Gs initial plus NSRT, natural log of pi upon pi initial, where Gs is the Gibbs energy of the solute particles in the solution. And then we can divide this thing by Ns, and that will give us the chemical potential, the molar chemical potential. Even though chemical potential is actually defined as a partial derivative, it's okay to just divide by Ns, and that will give us the chemical potential. So this equation, and similarly you can do for actual ideal gases, right? So for an actual ideal gas, this equation is of course true because we considered this to be an ideal gas and then made this equation work. Similarly, for the gaseous phase of this substance, so there's a dissolved phase and there's a gaseous phase. For the gaseous phase as well, you have this thing, and then you just consider the Gibbs free energy, the molar Gibbs free energy of the reaction. So in this case, what is the reaction? It's just the gas dissolving in the solution. So for that, our delta G will be mu subscript S minus mu subscript G, and we just found out what those are. So we can say delta G equal to delta G initial plus RT natural log of all of this. So this C by P, it's a reaction quotient for this reaction. And yeah, from there we actually just got Henry's law like that. So for equilibrium at some certain concentration, pressure, temperature, you need our concentration to be some constant times the pressure, where concentration of course is the concentration of the liquid substance, the solute in the solution, and the pressure is for the gas phase. And next we want to explain Raoult's law as well, but for that we will need much more information. So just this much, just normal thermodynamics is not enough. So instead we will have to go for the ideal solution model. So what is an ideal solution? It's any solution where the substances that make up the solution have molecules of the same size and have similar interactions with their own molecules and molecules of the other substance. And what that means is that if you mix these, the enthalpy change of that mixing, that will be 0 because the interactions are the same. So it doesn't matter wherever this small molecule is, because even if it's in pure substance, it will be the same bonding, and even if it's in the mixture, it will still be the same bonding, and that's why delta H mixing is 0. and because they are of the same size, you can say that number density, or you can say that the space that one molecule takes, right? So maybe that would be a better term to say, that thing is constant. And yeah, okay. And then we find out the entropy of mixing Na and Nb moles, sorry, molecules, not moles. For moles I will use small n. So what would be the entropy of mixing? We already know that the enthalpy of mixing is 0. What about the entropy? So for that we'll use the formula given by Boltzmann, which is k natural log of omega, when omega is like the number of states that a system can take, is really only well defined for changes in entropy, and that's what we will find. So we will find delta S mixing, which is this change A and B pure going to a mixture. So for that you need sigma mixture upon sigma A sigma B. And how do you figure out what that quantity is? You just consider a lattice of A and B molecules, and then just find out all the arrangements that the molecules can take. So for simplicity we'll just talk about the distinguishable arrangements, because even if we talk about indistinguishable ones, right, where we name all of the molecules, it will still turn out to be the same thing, because yeah, those permutations will cancel out each other. So that will still be still be the same thing, so don't worry about that. So what I'm saying, omega mix, yeah. So for the mixture, our omega, that is Na plus Nb factorial upon Na factorial Nb factorial, which looks like Na plus Nb choose Na, and that's a good interpretation, because basically we are choosing Na sides out of the total Na plus Nb. I mean, now the total is Na plus Nb, before they were separate. So out of those we are choosing Na sides for the A molecules to be put in. And then this thing sigma naught Na plus Nb, sigma naught is the, well, this is not supposed to be the entropy, so this is not the entropy. This is the number of states, is the number of states of a volume consisting of a single molecule. So which single molecule, A or B? Well, any of those, we are considering it to be the same. All right, and because they are the same, we can say that omega A is omega naught to the power of Na, and omega B is also omega naught to the power of Nb. And then this quantity, it works out good. So delta S mixing, that's now k natural log of Na plus Nb choose Na or Nb. And then we use the Stirling approximation to get a better form for this, and we finally arrive at this equation, that delta S mixing is negative R Na natural log of Xa, where X is the X is the mole fraction of A in the solution, plus Nb natural log of Xb. And similar thing can be done for multiple liquids, where this, instead of this, you will have Na plus Nb plus Nc factorial upon Na factorial Nb factorial Nc factorial, which is a multinomial coefficient. So you can do that. Okay, so now you know what delta S mixing is, and the good thing is that because delta H mixing is 0, you can find out what delta G mixing is in a similar way. So delta G mixing will just be negative T delta S, and that will be RT and all this quantity. And then we find out what's the chemical potential of A in this mixture. I mean, at least, yeah, you just find out what's the chemical potential. So it's defined as the change in the Gibbs free entropy system when you only change the number of molecules of a substance. So this will be partial G mixing upon partial Na. And then doing everything, we finally arrive at this thing, that the chemical potential of A in the mixture, that is the chemical potential of A, pure A, plus this quantity RT natural log of Xa. And we also know from before the calculations we did for the ideal gas that the change in the chemical potential of A as a gas in the gas phase, that is RT natural log of the ratio of the pressures, partial pressures in fact. So when XA equal to 1, its vapor pressure is P naught A because it's a pure substance, and yeah, we just defined it to be P naught A. And chemical potential molar of vapor is same as of liquid in equilibrium because it's an equilibrium, so the change in the Gibbs free energy must be 0, and that means the chemical potentials must be equal, right? Yes, and then we can use this fact to change some stuff, to change the chemical potential of the gaseous A when X is 1 to chemical potential of the liquid A. And yeah, that's nice. Okay, so now we get this equation, and we also have this equation. So delta the chemical potential of A in the mixture, that's as what we know is chemical potential of pure A plus RT natural log of XA, and the chemical potential of A as a gas, that is the chemical potential of pure A liquid plus RT natural log of the ratio of the pressures. And then subtracting these two equations, you get this equation, and this left hand side, it's the change in Gibbs energy, molar change in Gibbs energy. So for equilibrium, this left hand side must be 0, so then the thing inside the natural log, that must be 1, so Pa equal to P naught A XA, which is exactly what Raoult's law is. So now you might be wondering why we didn't take the change in the chemical potential of the liquid A due to change in pressure, because VdV minus SdT, that would be our dg quantity, but VdP, that thing is also non-zero, right? Because the pressure is in fact changing. We are changing pressure all over the equations. So why don't we consider that? The easy reason is that the molar volume of liquids, it's very small in comparison to the molar volume of gases. And yes, we always deal with molar volumes for chemical potentials. Don't get confused by the fact that maybe you have a lot of volume of liquid in the container and it's still at equilibrium, and then for that condition, how would these equations apply? It's the molar volume that you should consider. So the major contributions, it's only because of the change in the chemical potential of the gas phase because of pressure, and for the liquid, the major contribution is because of the change in concentration. Now putting X equal to 1, yeah, we get this equation, that delta G equal to RT natural log of P upon P naught, and then you have these two equations for two different temperatures. So for different temperatures, you have different delta G's for this pressure P, and you also have different P naught values. And you assume that the enthalpy and entropy of this reaction don't change too much on changing the temperature, not pressure. Which is why I took the pressure P to be the same in both of these equations. And of course, X is 1, so we are not changing the concentration as well. Okay, so now using delta G equal to delta H minus T delta S and dividing this thing by the temperatures respectively, you can get these two equations and then subtract the lower equation from the upper one, and you get this thing. So it's basically like the Van Hoff equation, just instead of delta H, you are putting the latent heat of vaporization in this case. And then let's talk about elevation in boiling point as we are at it. So in previous equation, if you put the second condition, which is for T2 and P02, wait, did I just, yeah, this is actually correct. Yeah, so let T2 be equal to the boiling temperature. So what is the boiling temperature? It's the temperature when the vapor pressure of the pure substance, it becomes the atmospheric pressure. That's how the boiling point is defined. So if T2 is the boiling temperature, uh, then that means that P02, that must be the atmospheric pressure. And let T1 be something slightly more than the boiling point. And because the temperature increased, we intuitively think that the pressure should also increase. So we say P01 equal to P atmosphere plus delta P. But then of course we can change delta P to negative values, so it doesn't make a difference. Where of course these changes are very small. And then doing a bit of approximation, some Taylor series expansion stuff, you finally arrived at this conclusion. This is the equation that we use for elevation in boiling point. I mean the easier equation, the easier version of it. Yes, right. So now you know how the pressure should change if you want to change the boiling point, or I should say if you want to change the temperature at which you have this vapor pressure. So what's delta P for that? Yeah, you get it. But that's not the main thing. That's not what elevation in boiling point is, because at this point we are not talking about boiling point when we say P plus delta P. I mean P atmosphere plus delta P. That's, and of course TB plus delta T. That condition is not for boiling. So now here's the condition. If we are putting some solute, a little bit of solute into the solvent, so now we are making it impure, how would the boiling point be affected by that? So it will boil when the vapor pressure will be equal to the atmospheric pressure, but we know how the vapor pressure changes when you put impurities in the solvent. So we know that pressure is just P naught X, where P naught is for the pure liquid, and in this case we want it to be equal to the atmospheric pressure. So you need P naught to be P atmosphere upon X, right? So for some certain temperature you have some certain P naught value. So for this new boiling point, whatever new boiling point you have, your P naught value, that vapor pressure, that should be the atmospheric pressure upon X. But we already know how the change in pressure works. I mean how it is correlated with the change in the temperature. So just putting that into this equation, you can actually arrive at a good conclusion. And yes, just keep doing this. And yeah, you also have to take the assumption that X is like very close to 1, because of course you're putting just a bit of solvent, sorry, a bit of solute in the solvent. Just read this because it's just a lot of maths and I don't want to explain all of this. So yeah, after doing all of this, you finally arrive at delta T approximately R boiling point squared upon LV, where it's like the latent heat of vaporization, times 1 minus X. And 1 minus X, it's the combined mole fraction of the solutes, because we consider X to be the mole fraction of the solvent. So we can write this like this, and then multiplying on the denominator and numerator by capital M, which is the molar mass in proper units. So it's mass per unit quantity of substance, like kg per mole, something like that. So if you multiply by that on top and bottom, you can convert xi to molalities with proper units once again. And finally we arrive at this equation. So you just rename this RTB squared M upon LB as KB. So now you know how to actually find KB once you are given these values. So from that we can say that delta T, which is the elevation in the boiling point, that is approximately this constant KB times the combined molality of the solutes. And similarly you have a depression in melting point when you put impurities into the solvent. So we already know that how the chemical potential changes when you change the mole fraction of the substance. So at constant temperature pressure, right, so for some certain temperature, some certain pressure, we are not changing with respect to pressure over here, we're just changing with respect to the concentration. So you know how the chemical potential of the liquid, I mean the liquid phase in the solution changes. What about the solid phase? So we consider the solid phase to be pure. Its chemical potential doesn't change, I mean not much, that is. All right, well, not much, uh, it doesn't change, that's what it is. Okay, so from that we can figure out what the Gibbs free energy, I mean how it changes at certain temperature pressure. Well, pressure is not even in these equations, so let's just don't think about pressure. For some certain temperature, how does the Gibbs free energy change with the concentration? And for equilibrium, of course, you want this Gibbs free energy change to be 0. So for that you just need uh, the Gibbs free energy when you have a pure liquid, right? That Gibbs free energy change for melting. You can figure out what that should be if you define xa naught to be the xa value when your delta gt is 0. Is that making sense? I think it is. So I'm just going to move forward. So for melting of pure substance, we say delta H and delta S are almost independent of temperature. For pure substance, for a substance with a particular X, you can say the same thing, but when you're changing the X, don't say that the entropy is constant. So yeah, and then just use the definition that delta G equal to delta H minus T delta S and divide by temperature, you will get this thing. Now when we have the melting point, the pure substance will have equilibrium for melting. So for that you just need delta H pure upon Tm equal to delta S pure, and then putting delta S pure as this value into the equation, you get this thing, the delta G pure upon delta G pure at some certain temperature T upon that temperature, that is the delta H pure, which is basically the latent heat of fusion, times 1 upon T minus 1 upon the melting point. But we already know what this quantity is on the LHS. Look, it's this. So putting this as this quantity on the LHS into this equation, you can get this equation. And then once again, you just say T is Tm minus delta T and xa naught is 1 minus x, and you do some maths and you get this equation. Cool. And then finally there's something called osmotic pressure, which was also in what was taught to us when we were learning this. I mean, we are learning this. Okay, so osmotic pressure. We know that a dilute solution, in that solution the solute can be thought of as an ideal gas. So for that solute you have the equation pi equal to CRT, where pi is the pressure exerted by the solute on the walls. So what's the pressure exerted by the solvent on the walls? Well, the total pressure experienced by the wall minus CRT, right? So it's basically that concept just applied to a specific configuration. So what is the configuration? First we'll just talk about a simpler configuration, and then I'll go to the actual thing. So just consider a column of this solution, and we just want to find and if A is open to the atmosphere, then what's the pressure at B? You have been given the height of this column, and you also know the concentration, the temperature of the solute, it's dilute. Can you find out what's the what should I say, what's the pressure experienced by the solvent molecules at B? That will be rho gh minus CRT. It was easy, right? Okay, now let's go to something a bit more complicated. where we are considering two of these columns, one with pure solvent and one with the solute in this. So as you can see, the left hand side of this semi-permeable membrane, which is over here, that thing, the water molecules over there are experiencing more pressure, and on the right hand side they are experiencing less pressure. So when we let the solvent flow, what will naturally happen is that it will flow from left to right until the pressures experienced by the water molecules become equal at this point, like this. And then we just find how that will work, what are the equations for these, and this is the equation. So you can figure out for what delta H this will be at equilibrium and stuff. Yeah, and then there's other configuration where you force where you basically are pushing down on the more concentrated side to keep the water from rising up. So by applying this extra pressure, you can make the pressure experienced by the water molecules on the right hand side container to be more, so that they would be equal. I mean, that pressure would be now equal to the pressure experienced by the water molecules on the left side, and that will mean that it will be at equilibrium, and that pressure is it turns out to be CRT as well. So the osmotic pressure is, as we called it before, pi, and it's basically CRT. So yeah, that was it. That was liquid solution. So yeah, it took quite a time, half an hour, but I hope you learned something that you didn't before. At least I did while writing this. So I'll see you guys in the next video.